the 50th term, this series gives us 49. And on the 51st term, this gives us negative 50. Now, these two seem very far apart away from each other, let alone 1/4. But I have a very good reason as to why this is true.
Can I have a question on modulo theorem?
Sorry?
On the modulo, can I have a
Okay.
question? A and n are two natural numbers, okay? A and n. So suppose a 3 and n is 6. 3 square is 9, modulo 6 is 3. So a square is equal to a basically, okay? Under mod 6. So I will say you a n. For that, can you say me an idempotent that a square is congruent to mod a under
Wait.
mod 9?
I can't hear you from... Wait, can you write this?
So these kind of elements are called idempotents whose square is equivalent with themselves. So now when I speak a n, can you say is there any idempotent or not? Or n equal to 8, you cannot find any idempotent from 2 to 7. Okay, 2, 3, 4, 5, 6. So is there any classification of those kind of n?
That's an interesting question. So if you don't know, I believe idempotent basically means applying the same information twice gives you the same result as if you applied it once. Firstly, before I begin my lecture, I would like to thank the Honorable Principal Kamal Astanand for inviting me here today. I cannot express how excited I am to be giving a lecture at the Honorable Ramakrishna Mission Vivekananda Centenary College. I'm so excited to see all of you here today. But before we begin today's lecture, may we please rise for the national anthem? Thank you. Oh, please stop talking, by the way.
Jana Gana Mana Adhinayak Jaya He Bharat Bhagya Vidhata Punjab Sindh Gujarat Maratha Dravida Uttar Banga Vindhya Himachal Yamuna Ganga Uchchala Jaladhi Taranga शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जय गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे
Okay. Thank you, everybody. Okay, simmer down. As Swami Vivekananda once said, the powers of the mind are like the rays of the sun. They illuminate if you focus them. So please focus on today's lecture. If you have one, please take out your paper and pen. In fact, I have a spare notebook and pen right over there if anyone needs it. All right. Has everyone taken out their notebook yet? If they have one, of course. Alright, so once again, sisters and brothers of India, thank you so much for attending my lecture, and let's begin. First, by talking about a few applications of number theory to get you hooked in. So it's a little bit hard to write like this instead of whiteboard, but I'll do my best. So, number theory. Okay. So, the biggest application of number theory is cybersecurity when it comes to computer science. So, if you want your data, like your pictures and your messages, encrypted, so that they are safe from anyone trying to eavesdrop or look at your conversation, so if you don't want anyone except the intended recipient to receive your picture, your text, your email, or anything else, cybersecurity will prevent that from happening. So, this is through something known as PSA encryption, which is an algorithm that has to do with primes. Essentially, it takes a number known as a semi-prime. A semi-prime is a number that is the product of two prime numbers, or numbers that have no proper divisors other than 1 in itself. So like 7, for example, 1 divides 7, 7 divides 7, but 2 does not divide 7. Cannot. So, a semi-prime would be something like 77, which is 7 times 11. 7 and 11 are both primes, as you can see. So, these semi-primes are relatively easy to factor when they're only something small like 77, but when they get big, then they can be very hard to factor. For example, take this example. So let's see. What's something that I could think of off the top of my head? Alright, so for example, something like, okay. So, let's say you want to factor 979. Can anyone tell me the prime factors of that? No one, right? That's pretty good. Because 979 is only 3 digits. So really not that hard to factor. It's, as you can see, just the product of, I can't get my pen over here, 89 times 11. Alright. And 89 and 11 are both prime, by the way. The reason that we're picking exclusively semi-primes is because if you pick something that is more than a semi-prime, i.e. it has more than those 4 factors that you've given it, then it's very likely that you can just guess a random factor, or it's more likely that you can just guess a random factor and it will be true. We're trying to keep the amount of factors to a minimum. So then you might ask, well, why aren't we using primes? Well, here's the thing. Let's see. Can I scroll on this thing? Okay, let's see. I'm going to have to use my cursor here. So, we start by taking some prime, semi-prime, let's say 77, and then your intended recipient gets one of the prime factors. Now, computers have perfected the algorithm of division a long, long time ago. So it would take seconds for your computer to recognize, well, milliseconds for your computer to recognize 77 divided by 7 is 11. The other prime factor needed to decode your encryption. But let's say that you have neither of the 2 factors because you're a hacker trying to look at someone else's conversation. So you have neither of the 2 keys, and the only way that your computer knows to find these prime factors, there were slightly better algorithms, but this is usually how computers do it. It's just by dividing through manually. Does 77 divide 2? No. That gives you, what, 38.5? So that's out of the question. Does 77 divide 3? No. That's going to give you about 25.67. Does 77 divide 4? Well, let's think about it. No. 77 doesn't divide 4 either. 72 does divide 4, and 72 divided by 4 is, well, let's see here, 24 times 3, it's going to be 18. So we have 18.75 over here, at least I believe so. 77 is not divisible by 5 either. You only need to test prime for this case, however, so we can leave 4 out. 77 divided by 5, for example, would be 15.4. 77 divided by 7, aha, finally, we found the factor, 11. And then your computer can find the next factor from there. But that took much, much longer compared to the division algorithm. If we were doing that with the 979 thing, it would have taken almost forever. And that's a lucky case because it has a low prime factor, like 11. What happens when you have two prime factors that are both high on the list, like 113 and 89? Or even worse, you have something that's not just 3 puny digits, but let's see, almost 30, like this. How do I, okay. Something that has much more digits. Like, how would you factor something like this? It would be infeasible for a computer to just divide through over and over. But even for a colossal number like this, a human could still easily divide this by one of its prime factors, although it would probably take somewhere around 20 minutes. But it would take years to find the prime factors of this just by brute force, or Eratosthenes' sieve, or whatever other algorithm that we have that is optimized enough to find the prime factors of this function. So this is the biggest use of number theory, and that's why I find it the most important for keeping all of our personal data safe. So now, let's get into something that isn't just number theory, but appears in a variety of fields. But it's most useful in number theory, which is why this talk is titled Number Theory. All right. Here we go, and here we go. If you have ever taken calculus before, especially calculus 2, you might remember the notion of infinite series. So these are essentially series that either converge or diverge. What does this mean? Well, first we have to get acquainted with the use of what's known as a limit. I really wish I could open up other applications on here. In fact, GeoGebra is right there, but I suppose not. So let's get a red color for this one. So essentially, what is a limit? Well, let's say we have a function right over here. This is f of x, not meant to represent anything in particular. So let's say we have some point over here which corresponds to an x value of a. And let's say that f at that point is equal to some number L. Essentially, the limit as x approaches a of f of x. Let me just. Is there an undo button? Of course there is. Let's see. Wait, what? Oh boy. Oh boy, what am I doing? Can't. Okay. Let's see. Let's try undoing this again. Oh gosh. See, these are the benefits of a whiteboard. Don't get nasty pop-ups about entering latex text. No, I can just undo it manually. Okay, there we go. So, see, I have no idea how to use technology. All right. So the limit as x approaches a of f of x equals L if, and only if, we have some interval with length 2 delta, so ranging from a minus delta to a plus delta. Sorry for the bad handwriting here. Please pardon me. Such that for any range we have, let's see, for any range a minus delta to a plus delta, the values of f of a minus delta and a plus delta, not plus, comma, A plus delta fall in between some L minus epsilon and L plus epsilon for all conceivable or all real. How do I get the pen to this corner? For all real delta and epsilon. This is just some fancy notation. It's for shorthand. You don't really need to worry about it. All right. So, this is the formal definition of a limit. You might think, well, why do we need it? Can't we see on the graph clearly f of a equals L? Why can't we just plug it in? Well, let's look at one graph where that's a problem. Like, which one? Okay. So I'm going to choose something like x plus 2 divided by what? Right. Okay. So let's just do something like x plus 2 divided by x plus 2 times x. Now, the thing is, for every other point, this looks like a normal graph of x because these two add up to the same number. So they just cancel out and you get x on the other side. But for x equals minus 2, it ends up being undefined because this will now give you the same number on top and bottom, but it's 0 over 0. We can't simply say that's 1. So it stays undefined here. So, however, we know that the limit as x approaches minus 2 of f of x is equal to minus 2 in that sense. So what does that mean here? Well, now we have to talk about limits approaching infinity. Essentially, what is a limit approaching infinity? So, sometimes we have a function where we get closer and closer and closer to a certain value, but we never actually reach it. So, these functions have a limit or a horizontal asymptote. So the limit as x approaches infinity of this function is going to be some finite number. Now, for most functions, this isn't true. Like exponential functions, let's see, just regular polynomials, cosine and sine functions, which while they are bounded between minus 1 and 1, they don't have a limit at infinity. So for most functions, this doesn't work. But for a select few, this does. Let's see, can I add a page? I probably can, right? Oh, here it is. See? I'm a IT master. Okay. Yeah, no. Okay. So, let's see. We did that. So now, let's talk about those actual infinite sums. Oh, I can write like this. That makes things so much easier. Scared that making contact would, make other marks. Alright, so infinite sums have been long considered to be a paradox. So, for example, in the 3rd century, or around 200, there was a man named Zeno, I think he was Greek, who came up with Zeno's paradox. Essentially, you have Achilles here. He's a man from Greek mythology, and he is very good at running. So let's say he runs at 10 meters per second, which is pretty fast. And then you have a tortoise. Tortoises are not normally known for running. So this tortoise would go at, say, 1 meter per second, which is still extremely fast for a tortoise. That's like a normal human walking speed. So Achilles decides to challenge the turtle to a race. Since the turtle was already confident from winning against the hare, the tortoise agrees. But the tortoise says, since you are so fast, I must get a 10-meter head start. And so it was. So now the tortoise is 10 meters ahead of Achilles. So, what happens? And we're not going to say the race is infinite. Let's say that the finish line is 100 meters away, all right? So who do you think is winning the race? Achilles, who moves at 10 meters per second, or the tortoise, who moves at 1 meters per second, but has a 10-meter head start? Who do you think wins? Well, of course, who is going faster here? Who is going faster, Achilles or the tortoise? Who is moving at a faster rate? Okay, so, yes, Achilles, the human, is moving at a much faster rate. Do you think the tortoise's head start will make Achilles unable to catch up? So who wins the race if the human moves 10 times faster, but the turtle has a 10-meter head start? Yes. Okay. So you might have reversed the paradox a little bit there, but here it is. So any reasonable person would assume that Achilles wins the race. And if you think about it, if you make a graph of their position function over time, so like this is position, and this is time, if you make a graph of their position function over time, you will see this blue graph is going to be the tortoise. So he gets a 10-meter head start. So this would be x plus 10. And then this is Achilles. And this is just 10x. So it will take Achilles 10 seconds to complete the race. But it will take the tortoise, because it moves at 1 meters per second but only has 100 minus 10 and 90 meters to cross. Where is it? 90 seconds to complete the race. And you can see, obviously, that Achilles must catch up to the tortoise at some point. And Zeno saw this too. But here's what he thought. Well, to catch up with the tortoise, Achilles must first reach the point where the head start happened. But once he reaches that point, which is 10 meters away, so it takes him 1 second, the tortoise has already moved a meter in front of him. This is 11 meters and this is 10 meters. So the tortoise is already here. But then, once Achilles catches up with the tortoise's second position, he will find that in the 0.1 seconds that it took him to move there, the turtle has already moved 0.1 meters. So now this is 11.1 meters. And then, once he moves to that head start, the tortoise will move further, and then further, and then further. So Achilles will never catch up to the tortoise, right? Is that true? So who wins the race now? Achilles or the tortoise? Did you misread it? Achilles is the much faster one, but no. It's okay. All right. So, let's see if we can maneuver into making a new page. Aha. Okay. So, what's the resolution to this paradox? Well, Zeno thought it would take an infinite amount of time. Cross 10 plus 1 plus 0.1 plus 0.01 plus 0.001, etc. So he thought this sum equals infinity. So it would take an infinite amount of time for Achilles to catch up with the tortoise. Or at least some amount of time that is larger than the time it takes for the tortoise to finish the race, 90 seconds. So Achilles must lose, right? Well, let's think about this sum. What is this? This is 11.11111 etc. Now, have any of you ever seen the decimal 0.1111111, etc.? Any of you? Yes, 1 over 9. So, given that information, what should this be? You're moving the decimal place 2 spots to the right. So then what should this value be? Yes, that is correct. So, this is really not infinity. It's just 100 over 9. But how do we prove that? Well, let's think about this series. From now on, we're going to use these terms for a series. So let's say we're talking about the series of natural numbers 1, 2, 3, 4, 5, etc. Then 1 is going to be called A1, 2 is going to be called A2, 3 is going to be called A3, 4 is going to be called A4, 5 is going to be called A5, and I think you see the pattern here. So, if we wanted to make a general explicit expression for AK, what would it be in terms of K? Yes. Okay. So, now we're going to do a similar thing here by using exponents. So, you will notice that the first term, A1, is 10 to the power of 2. The second term is 10 to the power of 1. The third term, wait a second. Oh, whoops. This is 10 to the power of 1. This is 10 to the power of 0. This is 10 to the power of minus 1. This is 10 to the power of negative 2, so on and so forth. So, in terms of K, what is this sequence? Sorry? Yes. Now, of course, I don't want just one person answering these questions. The rest of you have to be more active. All right. So, yes, the answer is 10 to the 2 minus k. So, how do we determine if a sequence does converge? That is, it has a finite limit at infinity, or the sum of all its terms over and over approaches some number that is less than infinity. Like in this case, where it approached 100 over 9. How do we quantify that? Well, let's see. Let's figure out this page button. All right. So, this is determined by this. The limit is k approaches infinity of the ratio of a of k over a of k minus 1. So this must be equal to n, which is less than 1. Or we can just say this must be less than 1. And if you really want to be a pedant, you can say should probably also be greater than minus 1. Alright, so let's test out the 10 to the 2 minus k sequence over here. So, what is a to the k for this sequence? Come on, it's right there on the board. Just say it out loud. What is 10 to the 2, what is a of k? Yes, it's 10 to the 2 minus k. So what is then a of k minus 1? It's not 10 to the... Yes, thank you. Alright, so then we get 10 to the 2 minus k over 10 to the 3 minus k is less than 1. Yes. So it should be pretty obvious that this converges. Now, let's talk about a series that seems like it should converge, but doesn't. 1 plus 1/2 plus 1/3 plus 1/4, etc. Now this is what is known as the harmonic series. So, as you can see, I don't think it's necessary to show you that a of k equals 1 over k. So then, testing it out on the formula, we get 1 over k over 1 over k minus 1, which is equal to k minus 1 over k. But that is equal to k over k minus 1 over k, which is equal to 1 minus 1 over k. Now, can anyone tell me what the limit of 1 over k is as k gets bigger? Yes. So you get 1 minus 0, so 1. 1 is not greater than 1, is it? So, that means that we cannot say the harmonic series converges. And in fact, it doesn't. If I remember correctly off the top of my head, it actually diverges and grows in a pattern similar to ln of x, or the natural logarithm of x. Let's add another page. All right, here we go. So now, let's talk about a more interesting series. So, you've already seen that 1 over k doesn't converge. What about 1 over k squared? By which I mean 1 over 1 plus 1 over 2 squared is 4, 1 over 3 squared is 9, 1 over 4 squared is 16, 1 over 5 squared is 25, etc. Do you think this converges? Aha, so most of you have taken Calculus 2. Yes, by the p-series rule, this does converge. Oh, I suppose it would not p squared, but x to the p, right, where p is greater than 1. So, now, you might know that this series converges. Well, you should know that this series converges, but what does it converge to is the bigger question. Oh, yeah, okay, right. But do you know why? Or have you just seen it? Sorry? Okay, let's provide the proof of why it's pi squared over 6. So to do that, we're going to have to start from what's known as So, what is the Weierstrass factorization theorem? Well, the proof is too long to go over today, but essentially, it gives you a way to make any function of one variable into a product, an infinite product, in fact, from which is a function of both the thing being summed over and the variable itself. So in this case, we're going to use this to infinitely factorize sine pi x over pi x, which looks a little bit like this, if I remember correctly. No, I can't draw it too well over here, but let's see. Yeah, that's my best estimate. So this will look like this, and then can't get the pen over here. F of n comma x would become 1 over n squared minus x squared. Alright, so now let's keep going. What we're going to do first is convert an infinite product into an infinite sum, because that's actually what we're looking to do today. And you might say, well, that doesn't look like what we were trying to solve. We were trying to solve for 1 over n squared, not 1 over n squared minus x squared, and that's right, which is exactly why I'm going to put a limit on both sides where x is approaching 0. So that's the same thing over here, but I don't have enough space to write it. So then, what is the first thing we're going to do? Well, we weren't trying to find the product of all of these. In fact, that probably approaches 0, but I haven't studied it because that's not the purpose. So, let's see. Let's open up a new tab once again. Alright. So, you have this function. So, the limit is x approaches 0. And what we're going to do, actually, is Does anyone know how to simplify ln of a times b? What is this? Louder. Yes. Okay. Good. So you have the natural log of a plus the natural log of b. All right. So that's an excellent answer. So does anyone know what we might use to convert this infinite product of something into an infinite sum of something? Oh, sorry, wrong symbol. So given this information, what can we do over here? Yes, we take the logarithm on both sides. So for example, if we were doing root 2 over 2 times root 2 plus root 2 over 2 times root 2 plus root 2 over root 2 plus root 2 over 2, etc. Now, we're going to be taking ln of root 2 over 2 plus ln of root 2 over root 2 plus over 2 plus ln of root 2 plus root 2 plus root 2 over 2, etc. Fun fact, this is actually a formula for pi. So, that's not what we're focusing on today, though. So, we're going to take the natural log of both sides. And now, we're going to do what we need to do. Now, I think after this rule, you should be able to deduce that ln of a divided by b is ln a minus ln b. So you get, sine pi x minus ln pi x is equal to the limit as x approaches 0 of, oh, why did I write a sum symbol over here again? This is actually kind of dumb of me, so let's just resolve my mistake. Clear, this is a product still. And then we made this a sum. And now you might be thinking, well, wait a minute, Saborno. I thought we were still solving now. I mean, your limit worked out nice and well, but I thought we were still solving for 1 over n squared, not ln of 1 over n squared, and this will be solved very, very soon. In fact, this will be solved right now once we take the derivative. All right, so taking the derivative of both sides, we still have the limit hiding in this corner. We have d dx ln sine pi x minus ln pi x. We'll work this one out next time or next step. And then we are allowed to exchange, actually, the sum and the derivative. Let me erase what's on that side, if that's fine with everyone. Okay. So this is going to be, what is ddn, I guess, no, ddx of 1 over n squared minus x squared. Is anyone willing, ln of 1 minus x, n squared minus x squared? Is anyone willing to come up and do it? Not, that's okay too. Please raise your hand, by the way, if you would like to do this. Raise your hand. Sorry? Oh, okay. There were some people trying desperately in the back to see this board. Oh? Okay. Alright, so I'm going to assume that's correct. I'm kind of sad that a math professor has the answer for all of their students, but okay, so we have n squared minus x squared on this side, and then since we're taking n as a constant, since we're differentiating over x, we can basically treat this like, well, this is going to be d dx of, this is going to be d dx of the thing inside, 1 over n squared minus x squared. So what is that going to be? Well, that's going to be, let's see, n squared minus x squared to the minus 1 becomes minus 1 times n squared minus x squared to the minus 2 times, by the chain rule, minus 2x. So I'm just going to cancel these negative signs out real quick. So we get 2, let's see, oh, right. So this parenthesis is 2x times n squared minus x squared to the minus 2. Now, it looks like there's more of the page down here if I scroll. Aha, I told you so. Okay. So we get n squared minus x squared times 2x over n squared minus x squared squared. So I think these should cancel out. And that just gives us 2x over n squared minus x squared on the other side. Alright, so we get over here. Now, since we're summing over n and not over x, and since this term is on the numerator, and it's not associated with any term relating to n, then I'm pretty sure all we have to do is just quietly factor this out to get what we got here again. So then, on the other side, we had what? Well, we were still going to differentiate it, so let's scroll back up. We had ln sine pi x minus ln pi x. And to Professor Chakraborty, please don't answer. Okay. So, can anyone tell me what this is? Sorry? Sorry?
Hello.
Okay. So what I'm hearing is 1 over sine pi x, okay?
Into pi into cos pi x.
Okay. Anything else?
Minus 1 by x.
Nice, okay. I'm actually relatively impressed. Oh, pi by x. Okay, I see. What? But just to be sure, because I don't remember that being... Yeah, I don't know. Other people are saying pi.
Because 1 by pi x into pi, 1 by x remains out.
Okay, there we go. So, this is your answer, right? Okay, just to be sure, let me do it myself. Because I'm pretty sure this is correct, but I have to be totally sure, so that I don't mess something up later on. So this is going to be cosine pi x, and then this is going to be pi minus ln of pi x. Well, that's just going to be 1 over pi x times pi. So, yep, that's totally correct. Thank you. All right. So, looks like whoever said pi over x forgot to apply the chain rule. So we get pi x cotan pi x minus 1 over x is equal to, on the other side, we're actually going to bring the 2x over in the form of 1, I don't know why it's doing that. 1 over 2x is equal to that sum on the other side. Please, why is it doing that? Please note that there was still a limit here, and I'm just too lazy to write it down. And now here comes the most crucial step of the whole thing. Now, that is going to be, what is it doing? T, okay, now what is it doing? T equals, yeah, just lagging out every time I try to move. Alright, T equals I times X. Let me actually scroll down for a second because this has also become filled. So now, why is this useful exactly? Well, it's because of something that leads from Euler's formula. E to the I theta equals cosine theta plus I sine theta. I think this is actually like Abraham de Moire's formula, but or whatever. So we get e to the I theta equals cosine theta plus I sine theta, where I is the square root of minus 1. So this variable substitution is very important. Why? Well, let's see what happens when we try making cotan pi x. Now the thing is, cosine theta is actually equal to, if I remember correctly, I cosine hyperbolic I theta, and that is equal to, in turn, by Euler's formula, e to the ix, or I theta I think we're using here, minus e to the negative I theta divided by 2, and sine I theta, which is equal to I sine hyperbolic theta, is equal to e to the I theta plus e to the minus I theta over 2. We're just going to replace all these thetas with x now. Oh, right, this is I sine h I theta. I'm sorry. Oh, I see. This is my mistake. I'm sorry. So, I switched them up. This should have been I sine theta, and this should have been sine h I theta. Alright, so now what do we get? Well, let's see what happens when we divide these two and divide these two. So this gives us 1 over I cotan theta is equal to I cotan hyperbolic I theta is equal to whatever that is. Yes? Really? Oh, right. That could be correct. Let me just drag my mouse over and do that. Okay. Okay, here we go. Alright, so then we get e to the I theta plus e to the minus I theta divided by e to the I theta minus e to the minus I theta. Alright, so that looks a little bit messy, but can anyone please tell me what 1 over I is? Okay, good. Alright. No one would be opposed to me canceling out these two, right? So we get minus cotan x. Oh, I just realized that I forgot to replace this. The cotan hyperbolic ix. Alright, and now, if t equals ix, then x should be negative it. So, what does that mean? Well, if we have, let's go up a little bit. We already had cotan, cotan pi x. So then, in terms of t, this would be cotan minus pi it. Now, this is not the cleanest thing ever, but wait a second. Ooh. Oh, yeah. Okay. So, now, let's try using this. So, minus cotan x is equal to e to the I theta plus blah, blah, blah. So, this gives us e to the I times minus pi it, alright, plus e to the minus I times minus pi it divided by e to the I times minus pi it minus e to the I times pi minus pi it. Oh, this is a negative, by the way. Alright, that's a lot of i's. So let's reduce that, because there are two i's in each one. So it should be not too hard. Wait, why is there an I here? Oh, this is just so this is just minus pi t. This is negative pi t. This is pi t, and this is negative pi t. Alright, there it is. And then we're just going to want to replace, where was it? Alright, the 1 over x that we got from over there with 1 over negative it, which in turn is just equal to it. So here we go. We have, oh, right. Yes. By the way, I actually forgot that we're multiplying this by 1 over 2x. So the denominator is actually 2x squared on the bottom. Now what is that going to give us? 2 times minus it squared, which is equal to 2t squared, times, well, minus I squared is going to be, yes. Yeah, okay, that's right. So we get e to the pi t plus e to the minus pi t over e to the pi t minus e to the minus pi t. And this is multiplied by now this is multiplied by a certain x, as you can see up here. Or, yeah, okay. So multiply by minus it, and then we have up here minus 1 divided by 2 minus 2 times t squared. So now, the essential part of this, because you really don't want to be the person who goes through the calculations, and by the way, note that this is now replaced by a positive t squared after exchanging the x for t. So now all you really need to know is that L'Hopital's rule, which I'll just add here for a second. L'Hopital's rule is used 4 times, which is probably exactly why you don't actually want to go through the computations. So, essentially, you take the limit as x approaches 0 of f of x divided by g of x is equal the limit as x approaches 0 of f prime of x over g prime of x. Oh wow, it's almost 351 when you look at that. So you utilize this 4 times in a row until it eventually reduces to this nice expression. The limit as t approaches 0 of 2 pi cubed t plus pi squared divided by 4 pi squared t 2 pi 3 squared. Wait, oh yeah, over 4 pi squared plus 6. Yeah, that seems about right. So, oh no, this is a t squared, and yeah, everything else seems good. So this is equal to the limit as t approaches 0 of the sum of n equals 0 to infinity of 1 over n squared plus t squared. Now we can actually plug t equals 0 into this without getting 0 over 0 back. So we get pi squared over 6 is equal to the sum of n equals 1 to infinity over 1 over n squared. Alright. So now we've explored strictly convergent series. Okay. But now, I think it's time to explore something a little more interesting than even the basal problem. Now it's time to explore divergent series. Now you might think, well, Suborno, why would it be interesting to explore divergent series? I mean, there's only 3 possible results. 1, it goes up towards infinity. 2, it goes down towards negative infinity. Or 3, it just keeps coursing in the middle with no way for us to find its actual limit. And that would be right if we took the ordinary definition of summation. Now, we're going to take technicalities that work for summations, but they also work for things that are not quite summations. That might seem vague, so let me give you an example of what I'm talking about. Let's talk about Grandi series, first explored by Guido Grandi, an Italian mathematician from somewhere in the 1600s. Think around Newton's time. So 1 minus 1 plus 1 minus 1, etc. So what would this converge to? Does anyone have thoughts?
First 1 is left, and then minus 1 plus 1, that will be 0. So it may be 1 time. And again you take first 1 and minus 1, that it look like 0. So that limit look like 1 or 0. So it will never converge.
Wow, that's a good answer. Now, that is appropriately titled Mazur's swindle, where you can, with some algebraic manipulations, make it look like this summation can be either 1 or 0. And that's exactly why we're not using algebraic manipulations. Well, we are, but in a different manner than just adding and subtracting them. So, you can make this look like 1 or 0, but with this summation technique, it's actually neither. So if you look at the partial sum function, which will define b of k as the sum of all terms ak from k equals 1 to, let's say this is some variable n instead. So k equals 1 to n. So you'll see the first partial sum is 1. Then you subtract 1, so it's 0. Then you add 1, so it's 1. And you keep going. So in a similar way to how sine of x has no limit as x approaches infinity, this series is completely bounded. Just like this blue graph that we're drawing over here. And yet, it still had no limit. That keeps bouncing back and forth between 1 and 0. But now, let me show you something. That's not what I wanted to show you. Alright, so let me show you something known as a Cesaro summation. Essentially, you should not think of this as a summation. So even though it's not an official title, I'll put pseudo summation in front. So this summation essentially works by taking the mean of all the partial sums. What the heck does that mean? Well, let's explore it on a simple example, like 1 plus 1/2 plus 1/4 plus 1/8. And I think it's pretty simple to show that this converges to 2. In fact, there's even that famous illustration where you take 1/2 plus 1/4 plus 1/8 plus 1/16 plus 132 plus 164, etc., so on and so forth. Doesn't really matter what's at the end. This is going to sum up to 1, then add that to 1, and that sums up to 2. So now, let's look at the sequence of partial sums. So that's going to be 1, 1.5, because it's 1 plus 1/2. 1.5 plus 1/4 is 1.75. Then we get 1.875, and so on and so forth. So it converges fairly quickly. But now, let's take the mean of the partial sums. For example, the mean of just these sums is going to be 1, because it's 1 divided by 1. But what about the mean of these two partial sums? Well, the mean of these two is 1 plus 1.5 divided by 2, or that would be 1. Let me think about it for a second. Right, 1.25. Where's my cursor? Okay, there it is. So we would have this being 1.25. Now, let's compare the mean of the first 3 terms. The mean of the first 3 terms is going to be, where is it now? Okay. 1 plus 1.5 plus 1.75 divided by 3. Now what is that? Well, that's 2.5 plus 1.75 over 3, or 4.25 over 3. Yeah, that's about right. Now, what would that be exactly? I believe it would be something around 1.416. Right. Okay. And then, if you take the mean of the first 4, I think I'm going to have to use a calculator for this one. So let's see. So we have 5, this is 2, this is 1, this is 1, this is 1, and this is 6. So we get 6.125. Love someone to check that is correct, but that's what I'm going with. So we get 2.0416. Wait, no. Oh, yeah. I'm supposed to be dividing by 4, not 3. Yes. Yeah, I'm going to need a calculator for this one, I think. Yes. So I'm just going to abbreviate that as 1.531. Now, as you can see, it's very slowly converging, but it still converges towards 2. Now, you might think, wait a second, this is just an alternate form of summation that converges even slower than we want it to. What could possibly be the use of this? Well, now, let's try it out on the Grandi series. What? Brought me back to step 1. Well, there's a bunch of empty space over here, so might as well. Etc. Alright, so now the partial sums are going to be, as Professor Chakraborty mentioned, 1, 0, 1, 0, 1, 0, 1, 0. Now let's take the mean of them over time. So this is going to give, and I'm going to draw a long arrow, 1. This is going to give, let me see, where is it now? Okay, maybe I shouldn't be choosing such light colors. This is going to be 0.5. This is going to be 2 over 3, or 0.66. Then this is going to be, let's see. Oh, yeah, this is 0.5 again, sorry. Then, the mean of the first 5 is going to be 3 over 5. So, let's see, which is 0.6. Then, the mean of the first 6 is going to be 0.5. Then, the mean of the first 7 is going to be, well, 4 over 7, which is, oh, thank you. Let's see, and where's my cursor this time? Point arg. Okay, now I just totally can't. Okay. Maybe yellow was not the best color to choose, but number 8 is going to be 0.5. Okay, sorry for the bad handwriting, but yes, there it is. So we have 1, 0.5, 0.66, 0.5, 0.6, 0.5, 0.571, 0.5. And it overall seems like it's just converging towards 0.5, 0.66, 0.5, 0.6, 0.5, 0.571, 0.5. So it's slowly getting closer and closer to 0.5, or 1/2. So we can say that the Cesaro pseudo summation I did not spell pseudo. Summation is equal to 1/2. Oh wow, you can scroll between page to page. This is some new technology right here. Alright. So now, this is a very cool looking tool. But there were some theories that need something better. Like 1 minus 2 plus 3 minus 4 plus 5 minus 6, and so on and so forth. What do you think this sums to? Anyone? A little bit louder, please. Yes. But once again, we can pull a pseudo summation out of the darkness in order to give us a sum. So, this is the Abel summation. But interestingly, this sum was not first solved by Abel himself, rather famous mathematician Euler, who we mentioned a little bit earlier. So, he said, right before summing this, 1 minus 2 plus 3 minus 4 plus 5 minus 6, etc. is 0.25. That may sound ridiculous to some of you who are reading this text. For example, on the 50th term, this series gives us 49. And on the 51st term, this gives us negative 50. Now, these two seem very far apart away from each other, let alone 1/4. But I have a very good reason as to why this is true. Now, you can use the Abel summation, but that's the longest way around it. I'll tell you the essence of what it is, though. Essentially, you have a function, f of x, and then probably n as well, and then you multiply that by some sequence a to the n, and it's going to give you the series out. Now, this series, 1 minus 2 plus 3 minus 4, etc., was really a subsection of the general series 1x minus 2x squared plus 3x cubed, or rather 1 minus 2x plus 3x squared minus 4x cubed, etc. Now, in this case, where f of x is just this, we have f of minus 1. This is 1 plus 2. You have 1 minus 2 plus 3 minus 4, etc. So essentially, f of x comma n is equal to nx to the n minus 1. Oh, wait, that looks a little bit familiar. But no, the power rule doesn't play a part in this, where x is just minus 1. So, there is this way around it, but I'm going to showcase to you an easier way because I think we might be running out of time. Now, that easier way is by taking the Taylor expansion of 1 over 1 plus x squared, or 1 plus x to the minus 2. So now, what is the Taylor expansion of this? Can someone tell me the equation for a Taylor expansion, centered at 0, by the way? Sorry? Okay. No, just in general. So like f of 0 plus what? Okay. Sorry? Wait, okay. I'm pretty sure what Professor Chakraborty is saying is correct, but I can't hear from here, which is a very bad thing. But yes, it is definitely very involved with the factorial. Oh, I see what. Okay. So, I believe he was saying something like this. Once upon a time, I actually learned why these Taylor expansions worked, but that's a lecture for another time. So this keeps going on. And now, this has a very unique form for its derivatives. So, for example, f of x, the 0th derivative is, well, you get this. f prime of x is equal to minus 2. Yes. And then f double prime is 6, 1 plus x to the minus 4. F triple prime is minus 24, 1 plus x to the minus 5. And as you can see, it continues kind of like a factorial, but alternating signs. So you get fn of x, where n represents the number of derivatives, is Yep, I can see that. Okay, so we multiply it by n factorial on the outskirts. This is actually n plus 1 factorial, I believe, but we're going to keep it standing as it is over there. So n plus 1 factorial out over here. And then we have 1 plus x to minus n plus 2. If I'm reading that correctly. Yes. So we get minus 1 to the n, 1 plus x to the minus n plus 2 to the n plus 1 factorial. Alright, so let's write that down. Oh wait, I can't do things like that. I'm going to actually take this off and scroll just like that. So now, once we plug in, we got to plug in x equals 0, because that's what the expansion is centered around, to get minus 1 to the n plus 1 to the minus n plus 2, which is just 1, and then n plus 1 factorial. So we get minus 1 to the n times n plus 1 factorial divided by n factorial. So what does that give us? Minus 1 to the n times n. That's correct. Yes, that should be correct. So, what is this going to give us then? Well, if we scroll up for just the tiniest bit. Aha. Alright. So, what is this going to give us? Minus 1 to the 0 times 0, which is just 0, plus minus 1 to the 1 times 1, plus minus 2 times, minus 1 times 2 to the 2, minus 1 to the 3 times 3.
Can you finish it in 15 minutes?
Yes, it's done almost. Etc. Which gives us minus 1 plus 2 minus 3 plus 4 minus 5 plus 6, etc. Almost exactly what we were looking for. Wait a second. Oh, right. We also have to include the x's. I forgot about that. So we get minus 1 times x plus 2x squared minus 3x cubed plus 4x to the 4th. Yes, right. Minus 5x to the 5, etc. And then we were doing this all for 1 over 1 plus x squared. Now, does anyone, except Professor Chakraborty, recognize what value of x to plug in to make this work? Okay. So we get 1. Wait a second. Have I made a... I think I made a sign mistake. Sorry?
Minus 1 whole to the power n into n plus 1. Minus 1 whole to the power n into n plus 1 factorial by n factorial. If we write n plus 1 factorial is equal to n plus 1 into n factorial. N factorial cancel out. So minus 1 whole to the power n into n plus 1. The result is.
Okay. So I think you're telling me that I missed this?
No. Into minus 1 whole to the power n into n plus 1. Second term.
What?
Power is correct. Yes, n plus 1.
Okay. I believe I made a sign mistake here, actually. Because if you plug in x equals minus 1, which is what's supposed to give it to you, then you get 1 over 0 on the other side. So yeah, I definitely made a sign mistake. Because this is supposed to be 1x minus 2x squared plus 3x cubed, etc.
The term will be n plus 1.
Okay. Oof. Okay. I don't know how I didn't see that. Right. So, can you come here and circle it for me? Thank you. Can't believe I made a sign. Thank you.
See here, this is n plus 1 factorial by n factorial.
Yes.
So this will be n plus 1 into n factorial by n factorial. So n factorial by n factorial will cancel out. So there will be n plus 1. That will
Oh, jeez. That's an elementary mistake, isn't it? Right. So then that gives us 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the 5. Wait, no. Etc. So then you just plug in x equals 1, and you get 1 minus 2 plus 3 minus 4 plus 5, etc. So then if you plug in x plus 1, you get 1 over 1 plus 1 squared, which is 1 over 4. And finally, I know you all are tired, so I'm going to finish this quickly. We can get to Ramanujan's legendary sum. So we already know 1 minus 2 plus 3 minus 4 plus 5 is equal to, so this is equal to 1 over 4, and we already know 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. is equal to 1/2. So how will that help? Well, let's say we have 1 plus 2 plus 3 plus 4 plus ... equals some number n. Then we subtract minus 4, minus 8, minus 12 from 6, minus 16. And I think it should be pretty apparent that this is minus 4n. This will convert it into 1 minus 2 plus 3 minus 4 plus ... equals minus 3n. But we already know this is 1/4. So n equals minus 1 over 12. But Saborno, how can a sum of positive integers be a negative number? Well, as Professor Chakraborty mentioned, it is extremely illegal to do these kind of algebraic manipulations on divergent sums, treating them as if they were real. So, for example, as he said, you can do this. And get 0. And then, does this mean that 0 is equal to 1/2? Of course it doesn't. It just means that you're not supposed to do these kind of algebraic manipulations. And this fascinating answer that you get is not really the sum of every single natural number, but it's useful in other contexts. So why are these infinite sums useful anyway? I don't know if we have much time left to discuss that, but that's mainly for Fourier series. Fourier series. So essentially, these series mean to approximate any straight line function with trigonometric curves. And yes, they use Euler's formula to do that too, bringing a bit of complex numbers into the mix, but we're not trying to focus on that right now. So, of course, it doesn't look completely straight for any given approximation, but the point is that the limit, or the infinite series of all of these trig functions, sine and cosine, with varying frequencies, is meant to converge to this one function. They can be used for several things, like Fourier transforms, which are essentially what Fourier series are used for. They can essentially, if you have an inverse Fourier transform, you can have this weird-looking wave and then separate it into different frequencies. And that's useful because many of the things in life tend to be waves. Like, for example, sound waves. So if you're using audio filtering on an editing software, the editing software may use an inverse Fourier transform on whatever sound waves are in the audio. This is an oversimplification, but in order to split it into low and high frequencies, and it may eliminate the ones that are highest. I know I'm not an audio engineer, but that's the one of the everyday uses of Fourier transforms, and in turn, in turn, infinite series. So, there it is. I think we got to everything that we wanted to this lecture. We had time for everything. The convergent infinite series, the divergent infinite series,
Okay, baby, let's finish it.
yeah,
And then you can go for Q&A.
right. The Ramanujan summation, and a brief overview of its applications. So, once again, that's it. Thank you, everybody, for attending today, once again.
From your childhood, how you started your life with math?
Oh, it was mostly because of the inspiration of my father. So he was a math student at that time, and I was very interested in seeing his work, even though I understood none of what it meant. I was inspired to start learning a little bit of math when I was 2 or 3 years old. I wanted to get in. I wanted to be in on what these symbols meant. So I started studying math a little bit. I started abstracting it. I was using whatever textbooks my dad had at home. And eventually I asked my mom to start teaching me. So one day, after she taught me for a long while, she was reviewing everything we learned. So she asked me, first we're going to review addition. So you know what 1 plus 1 is, right? I said, yes, 2. So Mom, if 1 plus 1 is 2, what is x plus x? And she was like, oh wow, really? You learned that fast? Of course, x plus x is 2x. Then then she asked me, all right, since you're so advanced, let's jump to multiplication. What's 4 times 3? And I said, well, it has to be 12, right? But Mom, tell me this. If 4 times 3 is 12, what is n times n? And she said, n squared. Wow, you're doing very well. So she was a little bit, surprised. So she called my dad over to start teaching me a little bit more formally. So he gave me access to all of the textbooks he had laying around, and he tried helping me as much as he could when it came to math. So I managed to learn lots of things under his care and his tutoring, and eventually managed to learn Calculus 1 and Calculus 2 at only 7 or 8 years old. And then, at that point, my dad said, nope, I can't help you anymore. I can't remember anything else. Too hard for me. So he consulted one of his professors, or his former professor, from a college called the City College of New York. And they agreed to help me. So we kept working and continuing until at last I was where I was with the professor. He said he couldn't help me anymore either because his schedule was filled. I think that was an excuse. So I reached out to many universities across the state, including a university called Stony Brook University and New York University. So over there, I talked to the professors, and that's who I'm learning from right now. So I'm learning about calculus, topology, geometry, and special and general relativity. Turns out general relativity doesn't really take too much math or physics to understand. Just a lot of your imagination, just like anything else in math and physics. So, once again, that's essentially how I started my math and physics career. I of course owe it entirely to my tutors, my dad, my professors, and my teachers. And without them, or without the environment that I was in, I would have never gotten this far.
Question? Can I have a question on modulo theorem?
Sorry?
On the modulo. Can I have a question?
That's okay.
Okay.
How will you enjoy your life other than math?
Okay, so I'll answer this one, then the modulo one can come. Okay.
Okay, I am saying let
Okay.
a and n are two natural numbers. Okay, a and n. So suppose a 3 and n is 6. 3 square is 9. Modulo 6 is 3. So a square is equal to a basically. Okay, under mod 6. So I will say you a n. For that, can you say me an idempotent that a square is congruent to mod a under
Wait.
mod 9?
I can't hear you from. Wait. Can you write this? So, I actually don't know if there's a special classification for numbers like this.
N cannot be prime, that's for sure. But when composite, how it can be? I know the answer for nilpotent. Actually, while doing the ring theory, the question arises in my mind, but no one could answer it.
No, I don't believe there's a classification for this kind of
Yeah,
number.
one must is this composite, but we have to find. Suppose 15 square under mod 20 is very easy to find. That's
Yes.
15, but this is a little bit harder,
Yes,
I think.
that's interesting.
So you can think of.
Let me think about this. I'd have
Suppose
to do
n
more
is
research.
divisible by some square of prime or composite in a special form.
Mhm.
Right.
So,
When you write 6, you have 3, but when you write 8, you don't have any choice left for 8. So what can be the ends?
let's see. So, n equals. Okay. So let me see
Except
if.
0 and 1.
So let me see if I can write this down. So, essentially, a squared is not congruent to a. So mod n. So let's see. What would that require? Well, that would require, let's see, a squared minus a to be divisible by n, or a squared minus a equals some number k times n. So a squared equals a plus kn. Oh, wait a second. Okay, so that means k times n has to be equal to a minus 1 times a for some k, for whatever k. So that means that either it's k equals, so that means either n equals a minus 1 or n equals a, unless a has a few factors. Unless a minus 1 has a few factors.
Yeah.
So yeah, this seems like too broad for any kind of classification, but it's a very interesting idea.
Yeah. Suppose n gives a 36, so you have to take time for finding the a. You cannot say it directly.
Well,
So I am working on
okay.
this basically.
So if n
Suppose
is
it's
like
36.
Mhm.
Now find some a that a square equal to a from 2 to 35.
Okay, so that can't be that hard, right? So let's see. So you can have, oh right.
If exist.
So let's say n equals a minus 1. So let's say a equals 36. Wait, no, but that's not the point. Okay. So let's say a equals 7. So then 36k is equal to 6 times 7. So 36k equals 42. And it should be pretty trivial to find that k equals... Wait a second. Oh, that is an interesting problem. Yeah, I think it's probably pretty hard to...
Not an instant kind of situation.
No.
I think it's very harder.
Yeah, that's
If
it.
it's lemma or something, I don't. This is a special question. I think that arises in my mind.
Yes, of course it is. So, it's only very special classification, I think. And that would also require either a squared minus a equal to n, which is very rare, or a squared minus a is greater than n. So then that's very specific. So that limits you to a small group of numbers. Like, for example, for n equals 36, if a squared minus a is greater than n, or 36, then for that to happen, must be probably 49 minus 7 is 42. So a has to be greater than 7. Okay. Yes, this is very interesting, but it might be too broad. Yes. That's fine.
Dear brothers, Subonno, I want a suggestion from you. Please tell me how poor mathematical students will improve, especially their algebra portions.
Poor? Oh, okay. So, a poor algebra student, I mean, you really have to imagine it. A lot of poor algebra students don't have a concrete visualization of what's actually going on in algebra class in their head. They think X and Y are just letters that have been reintroduced in numbers. So, a poor algebra student might want to visualize X and Y as actual quantities. So, like, you take X in, you equal it to some number. Y is just based on X. So you take that number, perform some operations. So you might multiply it by 2, subtract 3, and then you get Y. And then you can look at the patterns that happen when you increase and decrease X, and then that can be a function. Of course, there were lots more in algebra than just functions and variables, but that's, I think, the main thing that people struggle with.
Okay, thank you, thank you.
Oh, this is your pen.
Any more question? Any more question?
No question.
No.
Now the vote of thanks will give by our most revered principal Maharaj.
So very thanks to Mr. Subarnoji for his very elucidative discussion regarding this infinite series, convergence, divergence and related all matters, and also he started the Fourier series also. But it is, all things are very big. But outside temperature 41, AC could not work because tripping every time, because 41 they could not down this. So in this respect, this small boy, 12 years boy, is trying his level best to understand, to make them understand all regarding this infinite series and divergence and convergence, which are very tough things. And I am very much appreciating his effort in each way, just like only 12 years old. So we are very much express our I think regard for his talent. In his 12 years, he has gathered so much knowledge regarding this number theory and its higher applications. So with these few words, I once again thanks him, and also thanks his father also. He all times actually helping him. He also a good mathematics teacher. But due to his effort, this small boy actually growing up just like anything. So, and also his mother and elder brother not here, they are in US. I also express their this respect or regard to them for providing this Subarno for all way to develop in the mathematics. So I think he will, his passion, he will in future he will be a good mathematics student and as well as a good teacher. So it is very evident that in 12 years he is so much proficient in mathematics. So in advance, I think he will learn a lot of and contribute to the society, to the world, to the nation regarding mathematics. And it is a very, all you know that mathematics is a very prime subject. Mathematics is the mother of all learning. So anyone teach mathematics properly, so if he or she can contribute the knowledge society just like anything. So I do not speak up many words because the time over and they have to take lunch also. I tell them because after that they will take lunch. So with these few words I express once again thanks to both, and also thanks all you present here, and also participate in question and answer session, and also afterwards you connect with him through email, right? Through email you can connect for your question and query.